Let's walk through the second example, which is illustrated right here. Once again, U is the source. And step number 1 in the initialization is to include the source into the n prime set. And that is why you see U being here. Now, step number 2. That is to what? To go over all the nodes and see if it's adjacent to A. If it does, then we do this. Set the minimum distance to the node, to the link cost between the source and the node, and set the predecessor to the source. So who are the nodes adjacent to the source U? So we do have V and W and X here, right? V connected to U, W connected to U, and X connected to U. And therefore, dV should be the link cost of UV. 2 dW, link cost of UW. dx, link cost of UX. The predecessor is always the source, therefore U, U, and U. For these two nodes who are not adjacent to U, we write infinite, okay, which is the else here. Set the distance to those nodes, infinite. And to be precise, the predecessor for those nodes will be then also nil. So 2U, 5U, 1U, infinite, infinite. So therefore, okay, to fill in the first row, step 0, 2U, 5U, 1U, infinite, infinite. Now we then enter the looping phase. Okay, in the looping phase, what we do first is to find a node that is not yet in n prime, but okay, di is the minimum. So what di we have? We have 2, we have 5, we have 1, infinite, infinite. Which one is the minimum? Yeah, this one here. Therefore, what do? We include x, okay, into the n prime. And then we move on to the second step in the looping phase, which is to update the minimum distance to these j's that are adjacent to I, which is x, okay, in this iteration, and not yet in n prime. So let's find out the j first. X here is the I. So u, v, w, y are nodes adjacent to x, but u is already in n prime, so we'll discount u. So we just need to walk through v, w, and y and update the distance to v, w, y. So let's start from v. Okay, the old dv was 2, so which is this entry here. Now we need to find out the di plus cij. So di is this, being 1. Cij, so I is x, j is now v, so the link cost is 2. So the new dv there is 3. Is 3 better than 2? Well, not quite. So we'll just leave the entry as is, okay, for column V. Second neighbor here, second j is w. Okay, so original dw, 5. So 5 here. So these are the old ones for V. So what about di plus cij? Di is still 1, okay, and cij is what? 3 this time. Okay, so in a way, this new path they just discovered, the cost is 4. Is 4 better than 5? It is, therefore. Okay, we write 4 here, and the predecessor is now the I. Because this new path, okay, for destination W, the previous node is X. What about Y? The new path being discovered is this one over here. So 1 plus 1, which is 2. And the O, okay, O dy is what? Ooh, infinite. So 2 is definitely much better, right? And the predecessor, again, being X. Z is not connected, so we'll just, write the entry down. Okay, so we have 2u, 4x, 2x, and infinity. That should feel, yeah, the second row here, 2u, 4x, 2x, and infinity. And that completes step 1. And that takes us back, okay, to the second iteration of the loop, where we find another I, where the di is the minimum. But in this case, what we're seeing here is, whoa, 2, 4, 2. We do have a tie, so we need to break the tie by picking one of these. So let's suppose that we pick y, and therefore we include y into the n prime. So y here is the I for the second iteration. So again, we walk through all the nodes adjacent to y, which includes x, w, and z. But these nodes cannot be in n prime yet. Let's see, x is already in n prime, so let's exclude that. And then consider only w and z. So let's see, what was the dw currently? 2. Yeah, what is the new path we are exploiting here? It's this one here, isn't it? Okay, so 2 plus 1 being 3. Is 3 smaller than 4? Yes, 3. Okay, and now the predecessor to go to destination w is y. Nice. Okay, yet another shorter path to w. For z, okay, the all cost, infinite. Okay, exciting. Yeah, because the new path here, 2 plus 2, 4, is obviously better than infinite. So we should be seeing what? Okay, 3y, 4y being added. V not being directly connected to y, we'll just write the existing entry down. So 2u, 3y, and 4y should fill the third row. Okay, complete step number 2. And again, we come back to the step 1 of the looping phase, and we pick the node that has the smallest d. This time, it will be v to be included here. Okay. And to complete the fourth row, we take the second step in the looping phase. Go over oj connected to I, and I is this time v, so where's v? Right here. All right. So all the nodes adjacent to v, but not connected, not yet in the n prime. So u and x already in n prime. So let's exclude those. So the only node remaining is just w. All right. So dw currently 3. So what is the new path we're exploiting here? This one here. Okay, so cost being 2, link VW is 3. So total cost for the new path is 5. Is it better than 3? No. So yeah, we just write down the same thing. Okay. Z is not directly adjacent. Let's see. Yeah, B and Y already taken. So yeah, just 2 entries, 3y and 4y for w and z. And that should complete 3y, 4y. Yeah, yet another row. So we're again in step 1 in the looping phase. So w is obviously the next one to include into the n prime set. And w is right here. For all the nodes adjacent to w, v, x, u, y, z. Well, actually, all of them connected to w. But you know what? U, v, x, y are already in the n prime set. So it's just z remaining. We need to see if the existing cost is better than the newly discovered path cost. The newly discovered path is w, and the cost was 3. Predecessor of w was y, so it's this path here. So 3 plus 5, that is 8. Is 8 better than 4? Well, not. So 4y remain here. And that fills up the last row. And next is to what? Include z into the n prime set. And that iteration for step 2 is trivial because no nodes is remaining there and not in n prime. And so this is the complete link state derivation table for the second example. Now, let's try to build the Dijkstra shortest path tree again, right? So let's go over all the possible destinations. From z, the predecessor is what? Y. Y's predecessor is x. So x's predecessor, u. So then we don't have to do it again for x, y, because they're already in the tree. Predecessor of w being y, so right here. B's predecessor, yeah, simply u. So this here, okay, is the shortest path tree built from the Dijkstra's algorithm. And that's what you see. Yeah, the shortest path tree being built from Dijkstra. The forwarding table that we need to install in router U is this. For destination V, yeah, whatever the shortest path indicates, this link here between UV. But for all the rest of the destinations, yeah, this other link, UX link. And this is how, okay, we come up with the forwarding table after running the routing algorithm. Okay, so using Dijkstra, let's build the shortest path tree, and it's clear, okay, for the destination over this branch of the tree, take UV. For all the destination over this branch of the tree, take link UX.